Welcome back to Statistics. This is Dr. James Wood, and today is Class 14. We'll be discussing the standardized equation of the regression line. But before we do that, let's review the main topics from the last lecture. In the last lecture, we introduced the topic of regression and prediction, a topic we'll be covering for the next 2 weeks. We said that statisticians use the word prediction very broadly to refer to any assertion or guess about an uncertain event or fact. A prediction, in this sense, can be about the past, the present, or the future. A common prediction problem in statistics is to estimate an individual's score or value on a variable that's usually referred to as y. And as an example, we described several different strategies for predicting the weight of a young man named Waldo. We described three good strategies for predicting Waldo's weight. The first strategy we discussed is to use the group mean as an estimate when we're making an estimate about an individual but don't have much individual information. Statisticians recommend using the mean as an estimate because it gives us a good chance of being close to the truth. For instance, if the mean is 170, a lot of people have scores close to 170, or we can say a lot of people have weights that are close to 170. So if we estimate Waldo's weight to be 170 pounds, we have a pretty good chance of being close to the truth, even though we may not be exactly accurate. Statisticians say that the group mean is an excellent guess, unless we have information that will help us make a better guess. And what kind of information is it that will help us make a better guess? Well, the answer is a variable x that is correlated with y will help us make a better guess. So this brings us to the second strategy for making estimates, using conditional means. And this scatter plot shows conditional means for weight. Each conditional mean is for a subgroup of men who all have the same height. Men who are taller have higher conditional means for weight than men who are shorter. Now, it so happens that Waldo belongs to this subgroup of men who are 76 inches tall. The conditional mean for this subgroup is 223 pounds, and we can use this conditional mean as an estimate of Waldo's weight. In general, we get better accuracy if we use a conditional mean rather than the grand mean as an estimate. The grand mean is the mean for the entire group. It's different from the conditional means, which are based on subgroups only. Now, the third estimation strategy discussed in the last lecture was regression. Regression is very closely related to the strategy of using the conditional means. The regression line is a line that is drawn to be as close as possible to the conditional means. So here's how the regression line can be used to make estimates. We locate an individual's value on x on the x-axis. Waldo's weight is 76 inches, so this is his value on x. We find the prediction point on the regression line directly above the value of x. The coordinate of the prediction point on the y-axis is our estimate, which is called y predicted. For Waldo, y predicted equals 219 pounds. Now, Y predicted is just an estimate. It's our best guess. And there's no guarantee that it's completely accurate, but it's likely to be close to the truth. Now, we discussed in the last lecture three important details about estimates based on regression. The first was terminology. We said that the estimated value has several different names. The names used most commonly are Y predicted and the predicted value of Y. Second, we said that the coordinates of, uh, of a prediction point on the regression line are X and Y predicted. For instance, the prediction point for Waldo has an X coordinate of 76, which is his X value, his height. The point's Y coordinate is 219, which is his predicted weight in pounds. Now, third, we said that for a particular value of X, Y predicted is usually very, very close to the conditional mean, and that's intentional. Conditional means give good estimates and good predictions. So the regression line is meant to be close to the conditional means, so that the regression line also gives us good estimates and predictions. Now, one of the most useful things about the regression line is that it has an equation. The regression equation makes it very easy to predict Y. For instance, the regression line we've been talking about has this equation. Suppose we know that a man is 75 inches tall. By looking at the scatter plot, we can see the approximate value of Y predicted. But the equation gives us a quicker and more accurate way to find Y predicted. We plug in 75 in place of X in the equation, and when we do the algebra, we get an exact value of Y predicted, in this case, 210 pounds. Now, in the last lecture, we also learned these new terms. Y, or the criterion, are names for the variable we want to predict. X, or the predictor, are names for the variable correlated with Y that helps us predict Y. So Y is the criterion, X is the predictor. They're the same thing. Okay, so now we're ready for new material. Let's start today by talking about the unstandardized regression equation and the standardized regression equation. We'll talk about how they're different from each other and how they're similar. Now, this is a scatter plot showing the relationship of fertility to life expectancy in about 100 countries. Each dot represents a different country, or we could say an individual country. The x-axis represents fertility, which is the average number of times each woman in the country gives birth. The y-axis represents life expectancy, the number of years on average that the people in this country live. Now, as an example, the United States and Mexico are both up on the left-hand side, upper left-hand side. They both have relatively low fertility, well, about 2 births per woman, and they have high life expectancy, 75 years or more. On the right side of the graph are countries with high fertility, that is, they're high on X, and low life expectancy. For instance, here's Afghanistan, and here is Somalia. So ask yourself, looking at this graph, is the correlation between fertility and life expectancy positive or negative? The answer is that this is a negative correlation. Countries with high fertility tend to have low life expectancy, and countries with low fertility tend to have high life expectancy. And here's the regression line, and its slope goes down from left to right and is negative. Now here is this line's unstandardized regression equation. Y predicted equals negative 4.64 times x plus 82. And we can use this equation to find the predicted life expectancy by using the x variable fertility. For instance, suppose the fertility in a country is 5. That is, each woman, on average, gives birth 5 times. We can plug that number into the unstandardized equation. Then when we do the math, we find that y predicted equals 58.5. That is, we estimate that in a country with a fertility of 5, people live on average a little less than 60 years. Now, we can get the same estimate if we use the prediction point on the regression line. Or let's say they give the same answer, but the equation allows us to be sure of what the exact number is. If we just find the prediction point on the regression line, there's a little ambiguity about what exactly it is. We can see it's somewhere about 0.60, but we're not as precise as knowing it's 58.5. Now, the regression line also has a second equation, and here it is, the standardized equation. The predicted value of the z of y is equal to negative 0.80 times the z of x. Now, to see how this equation works, we need to turn this into a hybrid scatter plot that shows unstandardized and standardized values at the same time. So we'll hide the labels of the axes to give us more room, and we'll put x and y at the end of these scales to show that they represent the raw variables x and y. And now we'll add a scale showing the values for the z of x. Here are the mean and standard deviation of the unstandardized x variable. We can see that the mean fertility is 2.8, which is equivalent to a z-score of 0. So we'll put 0 here, under 2.8. The standard deviation is 1.4. So we'll put z equals 1, about 1 standard deviation to the right of the mean, and z equals negative 1 at the same distance to the left of the mean. And we can fill in the other z-scores the same way. Now we'll do the same for the z of the y-scores. The mean life expectancy is 69 years with a standard deviation of 8. So we'll put z equals 0 next to 69. We'll put z equals 1 and z equals negative 1, 1 standard deviation away from the mean. And then we'll fill in z equals 2, negative 2 also. So now we have a hybrid scatter plot, which shows both the unstandardized and standardized scales. So let's get an estimate for a country where the fertility has a z-score of 2. The fertility is actually about 5.5, but it's a z-score of 2 because it's 2 standard deviations above the mean. Now we can plug that number into the unstandardized regression equation and then do the math. And we find that the predicted z-score for y is negative 1.6. And we can see that the prediction point on the regression line gives the same result. The predicted z of y is negative 1.6. So a country where fertility is 2 standard deviations above the mean, that is, z of x is 2, has a life expectancy more than 1.5 standard deviations below the mean. So let's try it again. Let's make a prediction about a country where fertility is 1 standard deviation below average. That is, the z of x is negative 1. The United States and Mexico have fertility in this low range. So we can plug negative 1 into the equation, and we do the math, and we see that the predicted z of y is 0.80. And here's the result using the prediction point on the regression line. Now, I'd like you to get some practice doing this yourself. Here are the mean and standard deviation of fertility. These are the same numbers we saw a minute ago when we added the z-scores to the scatter plot. I'd like you to use them to make a couple calculations. The first calculation is not a regression prediction. Instead, I want you to calculate a z-score. What is the z-score of a country where fertility is equal to 5? So go ahead, make the calculations, and write down the z-score you get. And I'm going to give you about 30 seconds or a minute, somewhere in there, to find it. Okay, I'm about to give you the answer. If you need more time, just you can stop the video for a second and finish making your calculations. Okay, the answer to this problem is that the z-score is 1.57. And here are the calculations. Take a look. If you got it right, then you don't have to look at this. But if you didn't get it right, then you need to take a minute to look and see what happened. I'll go through it quickly. The z of x is equal to the deviation divided by the standard deviation, right? But we're talking about x. In the next line, the deviation is equal to the score, which is 5, minus the mean, 2.8. And then once we have subtracted one from the other, we divide that by 1.4, which is the standard deviation. And when we do the math, we get 2.2 divided by 1.4, which is equal to 1.57. Okay, now we're ready to make a regression prediction. If the z of x is 1.57, which we just calculated, what is the predicted z of y? Now, here's the unstandardized regression equation we got a minute ago. So go ahead, do the calculations, and write down your answer. What is the predicted value of the z of y? Okay, I'm about to show you the answer. If you're still working on it, you can stop the video for a second. But here's the answer. The answer is the z of y is equal to negative 1.26. And here you can see I worked it out so you can get it. It's z of y is equal to negative 0.80 times z of x. In this case, the z of x is 1.57. So the z of y is equal to negative 0.80 times 1.57. And when we do the math, that gives us negative 1.26. Okay, now let's take a look at the prediction point. The z of x is 1.57. So the predicted z-score of y is negative 1.26. Okay, now that we're here, I'm going to show you something. Here's our z-score of 1.57. It's equivalent to an unstandardized score of 5. Now I want you to watch the prediction point and the arrows when we switch to the z-score of 1.57. What I want you to see is that the prediction point and the predicted value don't change a bit when we switch between x equals 5 and the z of x equals 1.57. I'll do it one more time slowly. Here's the prediction when x equals 5. And here's the prediction when the z of x is 1.57. The prediction point and the arrows don't change at all. So this tells us something about the unstandardized regression equation and the standardized regression equation. They both use the same regression line. They both have the same prediction point. And they both produce the same predicted value of y. The only real difference between them is that one equation uses the unstandardized coordinates of the points, and the other uses the standardized coordinates. Okay, so these two equations, the unstandardized and standardized regression equation, are really telling us the same thing, but one uses raw scores, the other uses standardized scores, or you could say z-scores, since standardized scores and z-scores are the same thing. Okay, now at this point we're ready for some new terminology. This is the unstandardized regression equation we've been working with. Unstandardized, but for when we're using raw scores. This number is called the unstandardized slope. It's also called the unstandardized regression coefficient. So it has two names, and you need to know both names because statisticians use both of these names. The algebraic symbol for the unstandardized regression coefficient is the letter b, lowercase b. This number is the unstandardized intercept. And its algebraic symbol is the letter a, lowercase a. Now, there's something here that may be confusing you. The slope is b, and the intercept is a. Now, you probably learned in algebra class that in the formula for a line, m is the slope and b is the intercept. And that's what every algebra textbook says, and they're right. But for standardized regression equations, it's different. B is the slope and A is the intercept. And that's what every statistics textbook says, and it's been like that for 100 years. And it's always confused students, but that's the way it is. I'm sorry for the confusion, but it started 100 years ago, so I'm not exactly responsible. So to sum up, here's the unstandardized regression equation. And here it is written in mathematical notation. The predicted value of y equals b times x plus a. Okay, now let's talk about the standardized regression equation, which uses z-scores. This number is called the standardized slope, and it's also called the standardized regression coefficient. It has two names, you need to know both of them. The mathematical symbol for the standardized regression equation is the Greek letter beta. Now I know what you're going to ask yet next. What is the standardized intercept? Why isn't there any there? In a regression equation, in a standardized regression equation, the standardized intercept is 0. Always. And we'll learn more about that as we go along, but it's always 0. But it's never shown because it's unnecessary. It doesn't add anything. Negative 0.80 times z is equal to negative 80 times z plus 0. The little hat over the y tells us it's a prediction, an estimate. Okay. So the standardized regression equation is always written like this, without the intercept. The intercept is there, and it equals 0. But it's an invisible presence, like a guardian angel or Casper the Ghost. So to sum up, here's the standardized regression equation, and here it is in mathematical notation. The predicted z of y is equal to beta times the z of x. So now we're ready to learn two essential facts about the standardized regression equation. I actually think they are super cool. So here's the regression line we've been working with and its standardized equation. And I have two questions for you. Here's the first question. What is beta? Okay, you got it. I'll give you a little hint. Beta, the Greek letter beta, is the mathematical symbol for the standardized regression coefficient, or we could say the standardized slope. So I'll repeat now. What is beta? Let's put it this way. What is it equal to? What number is it equal to in this example? Okay, ready? Since there's only one number there, maybe you guessed that. Beta is negative 0.80, the standardized slope, or the standardized regression coefficient. Okay? So if I ever ask you, if I ever give you a standardized equation and say, what's beta, right? There it is. It's not going to be negative 0.80, but there's going to be a number that's multiplied times the z of x, and the number that's multiplied times the z of x is the slope, and that's beta. Now here's the second question, okay? What is the correlation between x and y? Now put another way, what is the correlation between fertility and life expectancy in this scatter plot? Okay, well, that was a mean question. I was messing with you because I haven't told you what the correlation is. But the answer is going to surprise you, and it's what's cool. The correlation of x and y is negative 0.80. It's the same as beta. And it's no coincidence that beta is negative 0.80 and the correlation is negative 0.80. In a standardized regression equation, beta equals R. Always. Wow. So beta is the slope. So the slope of the standardized regression equation is equal to R. Always. On the one hand, now think about it. This is kind of amazing and unexpected. And I think the people who first came up with regression were surprised by finding this too. On the one hand, you have the average cross product of the z-scores, which we call R, or the correlation coefficient. On the other hand, you have the actual slope of the of the standardized regression line. So you have the slope of the standardized regression line. And these two numbers turn out to be the same. Now, I really don't understand why it is they should be the same, but they are. It's one of those little miracles. So here's the equation for the standardized regression equation. The predicted z of y is equal to beta times the z of x. And this equation is equivalent to it. The predicted z of y is equal to r times the z of y. So this is the essential fact one. I'll call it essential regression fact, that these two equations are equivalent. And I'm going to call this the magic formula, not only because it's amazing, but because it turns out to be so useful. So let me show you one way that the magic formula is useful. I'm going to show you how to solve regression problems in which the predictor and criterion are both z-scores. In the example I'll use, we're given the information that the correlation of midterm grades with final exam grades is 0.50. We're also given the information that Isabel had a z-score of 1.50 on the midterm. Now, here's the question. Estimate Isabel's z-score on the final. Oh, that sounds so hard, but it turns out it's just a cinch. It's really easy if you use the magic formula. Now, before beginning a regression problem, remember it's always a good idea to make sure you know which variable is the criterion and which is the predictor. In this problem, the criterion, the variable we want to predict, is final exam grades. Actually, final exam grades expressed as z-scores. And the predictor that will help us predict the criterion is midterm grades. Now, here's the information that I gave you a minute ago. The correlation of the midterm and final grades is 0.50. Isabel's score on the midterm, that is on the predictor, has a z-score of 1.50. Now we're going to use the magic formula to estimate Isabel's score on the final. First, we see that R equals 0.50. So we'll substitute that value into the magic formula. Next, we see that z of x equals 1.50. So we'll substitute that into the formula. Then we'll do the algebra. It's not hard. 0.50 times 1.50 equals 0.75. And this is our answer. It's Isabel's predicted z-score on the final. Isabel's predicted z-score on the final is 0.75. I told you that's easy. I mean, right now you might be a little confused because it's the first time you've seen it, but think how easy that was. You just took her z-score on the midterm, multiplied it times the correlation coefficient, and it gave you her z-score on the final. Now let's do another problem, but this time I'm going to stop and ask you to as we go along. For this problem, the correlation of midterm grades and final grades is 0.40. Now this is not the same class that Isabel took. This is another class. Gabriel had a z-score of 2 on the midterm. So here's what we want you to do. Predict Gabriel's z-score on the final. Now, for this, the criterion is final exam grades expressed as z-scores, and the predictor is midterm grades, again, expressed as z-scores. And here's the information I just gave you. Gabriel's z-score on the midterm is 2. The correlation of midterm grades with final grades is 0.40. And now here's what I want you to do. Go ahead and write down your answer. What is Gabriel's predicted z-score on the final? What is the z of y? Okay, if you got it, if you don't have it, I'm about to tell you the answer. If you don't have it and you're just working on it, hit pause on the video and then come on back. So the answer is that Gabriel's predicted score on the final, z of y, is 0.80, 0.80. Now, this can be a little difficult the first time you do it, so I'll work it out for you. We're going to use the magic formula. Remember, if we're trying to predict the z of y from the z of x, we always go to the magic formula. R equals 0.40, so we substitute that in. The z of x equals 2.0. That is, on the midterm, Gabriel's z-score was 2, which is pretty good, right? That's what, 97.5th percentile. So we substitute that into the formula. And then we just do the algebra. And we get that the predicted value of z of y is 0.80. So 0.80 is Gabriel's predicted z-score on the final exam. Okay. Now, I'm going to be showing you other uses for the magic formula, but before I do, let me show you the second regression fact for the standardized regression equation. So let me show it to you. Now, here's the hybrid scatter plot we've been using as an example. And now I'm going to draw 2 lines and a dot on it. First, I draw a vertical line where the z of x is equal to 0. In other words, this line is at the mean of the z of x, and of course it's at the mean of x. Okay? Next, I draw a horizontal line where the z of y is equal to 0. So this line is at the mean of the z of y and at the mean of y. Finally, I draw a dot, a green dot, where the 2 lines cross. Now, what is the name of this dot? Okay, give yourself a pat on the back if you guessed that this is our old friend, the point of averages, the most important point on a hybrid scatter plot. And you notice the regression line goes right through the middle of it. That's no coincidence. The point of average, the regression line always goes through the point of averages. Always. And this is essential regression fact 2. Now, this 1 and 2, I made up those numbers. Other teachers may not call them essential regression fact 1 and 2, but I'm calling them that to know how important these two facts are. The standardized as you remember, we covered this before, the standardized coordinates of the point of averages are always 0, 0. The regression line always goes through this point. So that means that the point with standardized coordinates 0, 0 is on all regression lines. The unstandardized coordinates of the point of averages are the mean of x and the mean of y. In this particular scatter plot, the means are 2.8 and 69, so the unstandardized coordinates of this point are 2.8 and 69. The regression line always goes through this point. So the point with unstandardized coordinates equal to the means of x and y is on all regression lines. It's the same point. It's just the point of averages. Now, you can see why earlier in a prior lecture we said that one of the reasons that the point of well, now you can understand one of the reasons why in the earlier lecture I said that the point of averages is the most important point on a regression line. When you draw a regression line, it has to go through the point of averages. Now, we'll be using this essential fact about the point of averages in the future, but for the meantime, let me go back to the magic formula. A minute ago, I showed you how the magic formula can be used to solve regression problems in which the predictor and criterion are raw scores. I'm going to show you how the magical formula can be used to solve, wait a minute. No, a minute ago I showed you how the magic formula can be used to solve if the predictor and criterion are z-scores. Sorry, I misspoke on that. But next I'm going to show you that that same magical formula can be used to solve regression problems in which the predictor and criterion are raw scores. So we're given a lot of information here about a midterm and final exam in a class. We're given the mean and standard deviation of the midterm, 75 and 10, and we're given the mean and standard deviation of the final exam, 76 and 8. And we're told that the correlation between the midterm and final is 0.50. Now, suppose we're told that Carla scored 90 on the midterm. So here's our problem. Estimate Carla's grade on the final exam. Huh? This sounds impossible. It's not. It's not. Now, first of all, as usual, it's a good idea to make sure we know which variable is the criterion and which is the predictor. In this example, the criterion, that's the one we want to predict, is the final exam score. The criterion is the raw score this time, not the z-score. Remember a little while ago we were looking at z-scores. This time it's raw scores. The predictor is the midterm grade. The midterm grade is the grade that helps us to predict the criterion. And again, for x, we're interested in the raw score. So here's the background information that we're given. And I showed it to you a minute ago. The means and standard deviations of the midterm and final and their correlation with each other. And here's the information we have about Carla. She scored 90 on the midterm. Now we're going to use this box here at the top to keep track of what we do in solving this problem. Here's how we begin. We know that Carla scored 90 on the midterm. That's our starting point of x. So we write 90 up here for x. So now we have one number filled in this box here at the top. Now we have to fill in the other numbers one by one. And we're ready for the next step. We're going to use x to find the z of x. Now, take just a moment to ask yourself, how would you turn a raw score of x into a z-score of x? Okay, you're right. You probably got this. This is the form. We're going to use this formula, and this is the formula you've used maybe 100 times so in this class. So it's nothing new, and it's probably getting pretty easy for you. The z-score, in this case, the z-score of x, equals the deviation divided by the standard deviation. The deviation equals x minus the mean. So we substitute x minus the mean for the deviation, and then we do some substitutions. First, x equals 90. We were given that information. So we substitute 90 in place of x. The mean of x equals 75. So we substitute 75 in place of 75 in the formula, in place of x in the formula. And finally, the standard deviation is 10, so we substitute that into the formula. And now we just do the algebra. You can see how it's going to turn out. The z of x equals 1.5. So if the z of x equals 1.5, we'll write it up here. We put that into the box. Now we're ready for the next step. Remember, we're trying to fill in all the numbers in this box. And the next step is to use the z of x to calculate the predicted value of the z of y. And how do we do that? Aha, you know what we do. If we start with z of x and we want to get the predicted value of the z of y, we get to use the magic formula. So here it is. I told you this thing is incredibly useful. The predicted z of y is equal to r times the z of x. And we can fill in this formula by substitution. The z of x is 1.5, so we substitute 1.5 into the equation. R, we can see at the bottom, r is equal to 0.50, so we substitute that into the formula. Look at that. And now we just do the algebra. 0.50 times 1.5 is 0.75. So we put that into the box. We're getting pretty close now. We have 3 of the 4 numbers that we need in that box at the top. Now we just need to transform the predicted z of y into y predicted. In other words, we're just going to transform a z-score into a raw score. And that's something we've been doing for months at this point in this class. So think a second. How do you transform a z-score into a raw score? You know this. You do know this. Okay, here's the formula we use. The raw score equals z times the standard deviation plus the mean. Aha. So we just have to plug in the numbers now. The z-score we're working with is 0.75. So we substitute that in. The standard deviation is 8, so we plug that in. Now, incidentally, because we're dealing with the z-score of y, we have to be careful to use the standard deviation of y and not the standard deviation of x. Next, the mean of y is 76, so we plug that in. And now we just do the algebra. So go ahead, I'll do the algebra for you. Here's how it works out. 0.75 times 8 is 6. So we have 6 plus the raw score equals 6 plus 76. And that gives us that the raw score is 82. And we put that into the box. Wow, we did it. Y predicted is equal to 82. So this is our estimate of Carla's grade on the midterm. There it is. So let's summarize what we just did. We started with x equals 90, Carla's score on the midterm. We transformed that raw score into a z-score, and we did that using a formula you know very well now at this point in the class. Then, there it is, using that formula. Now, why did we transform the raw score into a z-score? There was only one reason. We wanted to be able to use the magic formula. The magic formula is designed to work with z-scores. So that's why we started by taking the raw score and turning it into a z-score. Then our next step was to take the z of x and use it to predict the z of y. And to do that, we used the magic formula. And finally, we took the z of y predicted and transformed it into y predicted. And to do that, we used this formula that you know very well now because you learned it a lot earlier in the class. So let's sum up. How do we solve regression equations? How do we solve regression problems for which the predictor and criterion are unstandardized scores? What we really want to do is use the magic formula. But the magic formula is designed to work with z-scores. So if we have an unstandardized x score, that is a raw score, we begin by transforming it into a z-score. Then we use the magic formula to get our estimate of y, of the z of y. And since that estimate is a z-score for y, we have to transform it back into an unstandardized score for y. Okay, now we're going to learn another thing, how to solve regression problems in which the predictor and criterion are percentiles. Now it turns out that the method for solving this kind of problem is very similar to the method I've just showed you for raw scores. First, we transform the predictor, which is a percentile, into a z-score. Then we use the magic formula to get an estimate. Then, because this estimate is a z-score, we transform it back into a percentile. So there are 3 steps that are very similar to what we did with raw scores. So the underlying strategy is to momentarily transform a percentile into a z-score so we can use the magic formula. And then after we've used the magic formula, we switch back to a percentile again at the end. So now here's an example. We're given this information. The correlation of midterm grades with final exam grades is 0.50. We're also given the information that on the midterm, Misty scored at the 95th percentile. And here's the problem. Estimate Misty's percentile on the final exam. Let's begin, as we always should, by identifying the criterion and the predictor. The criterion is Misty's percentile on the final exam. There's no standard abbreviation for this, so we'll refer to it as the Y percentile, since Y is always our criterion. The predictor is Misty's percentile on the midterm, and we'll refer to this as the X percentile. So here's all the information we've just been given. Misty's midterm grade was at the 95th percentile. The correlation of the predictor and criterion is 0.50. Now, how are we going to solve this? Well, we put this box up here at the top. It's very much like the box before. We're told that Misty is at the 95th percentile on the X variable. So we'll put that number in the table. We now have a starting value, a percentile. And we need to transform it into a z-score so we can use the magic formula. So how do we transform a percentile into a z-score? If I told you somebody scored at the 95th percentile, how do you figure out their z-score? Okay, you probably got it. That's right. You use the table that gives the percentiles for z-scores. Now, I did that for us. We used the table, and I found that the 95th percentile is equivalent to a z-score of 1.65. So we'll write that here. Now, normally, you'll have to do this for yourself, but we're going quick today. So just take my word for it. A 95th percentile is equal to a z-score of 1.65. Now next, we need to use this z-score to get the predicted value of the z of y. And how are we going to do that? Okay, hope you got this. Right, we're using the magic formula. I told you, it's a magic formula. So we plug in the z of x over here. We plug in r here. And we do the algebra, and we find that the predicted z of y equals 0.825. So we put, that's about equal to 0.83, so we'll put it up here at the top. When we round it, if we're rounding to the second decimal point and 5 is in the third decimal position, we'd go up. So at least in this class. In other classes it might be different, but 83. So we still have to transform this z-score, 0.83, into a percentile because the problem asked us for a percentile. So how do we do this transformation? If you start with a z-score and we need a percentile, how do you do that? That's right. We just use the same table again. And to save us time, I checked the table. A z-score of 0.83 is equivalent to the 80th percentile. And I've written it up there. And that's the answer. Misty's predicted percentile on the final exam is 80. The best prediction we have is that she'll score at the 80th percentile. So let's summarize what we just did. We started with Misty's midterm score at the 95th percentile. We converted the percentile to a z-score for x using the table. We used the z of x and the magic formula to estimate Misty's predicted z-score on the final exam. And then we used the table again to transform the z-score into a percentile. We converted it into a percentile because the problem asked for a percentile. And that was our answer. Okay, now we've covered a lot of territory here today, and uh, I congratulate you. There was a lot here, but the more you think about it and do those homework problems, be sure to do them. It'll all fall into place, and you'll see that how the magic formula makes your life so much easier when you're doing prediction problems in regression. Whether you're if you start with a z-score, a raw score, or percentile, it's usually pretty easy to find the predicted value of the predicted y value. Okay, well, it was good talking with you, and we'll see you again at the next session.